Hello everyone, I'm Jinlong. Today my partner Wei and I are going to talk about our research, stock price prediction under anomalous circumstances. Stock price prediction has always been a question that everybody in the financial market cares about. Financial professionals has been trying to explain the market and predict the future stock prices using financial tools and models for decades. Recently, some prediction methods from data science and perspective has been proposed and become more popular over time. So let's start with what does it mean to predict stock prices from a data science perspective. First, the underlying logic is that we assume that there is a pattern in the stock market. Then we try to find the pattern by analyzing data, right? This pattern could be supported by economic situations, people's trading behaviors, etc. This is not an incorrect assumption to make, but maybe we need to pause for a second and think about it. Can one single model fully explain the phenomenon that we observe in the real-world stock market? Maybe the answer is no. Let's look at an example. Since this February 20th, the stock market has been crashing. Was this caused by a recession? No, it is caused by the oil price war and the COVID-19. Can oil price war and COVID-19 be predicted by looking at past data? I don't think so. So the stock market is full of this kind of huge uncertainty. And sometimes it is dominated by the information effect. However, as you can see in the graph, there is some kind of pattern even when the market is crashing, like it will go down by a lot, then rise a little bit, then go down by a lot. What we are trying to learn about are these patterns. In other words, we are trying to look at how the stock market will behave after the anomalous circumstances happened. Now let's talk about our methodologies. For stock data, we pick 100 stocks from 20 industries, 5 stocks per industry. We choose these stocks because they generally have higher prices and trading volumes, i.e., they have better liquidity, which means that they are more stable than other small stocks and more representative. How do we find the anomalous circumstances? The answer is outlier detection. Anomalous circumstances are usually where a general prediction model fails to predict accurately. Thus, we first run a REMA, which is a time series prediction model on our data. Then we look at the point where the studentized residual is bigger than 2 and flag them as an outlier. Why not bigger than 3 as a standard defined? Because that way we'll have a super small data size. For each stock, we train a model with either 2017 or 2016 adjusted closing prices and then use it to predict the stock's adjusted closing prices in 2018 and 2019. There is a sample prediction of Tesla and outliers that we flagged. Basically, we considered 3 days before and after the outlier day as our anomalous periods, and then we continue to study these cases by training new models. To further support our models, we introduce sentimental analysis. We use an Reddit API to download all comments from these 5 subreddits among the designated date, according to the designated date, and stock symbols. Then we concatenate these comments and do sentimental analysis via Vader, which gives us a numerical score to indicate that the sentiment of the comments. I think we should of the comments. We try 2 classes of the models to predict the stock adjusted closing price during the detected anomalous periods, LSTM and Ceremax. Let's first talk about the LSTM model we implement. This LSTM is basically a usual one plus a sentimental cell. As you can see in the graph, what's inside the box is a standard LSTM model, and what's outside is a memory cell for sentiments. We basically implement it as it is proposed in Yojin and the loss paper, but there are slight differences. First, we did not use the loss function proposed in their paper since we do not need to calculate the loss function for sentiments. Instead, we choose to use a L1 loss function and MAE as our loss. Our S is not initialized as 0. The input size and the hidden size are both 8 and the output size is 3. We also choose Adam as our optimizer. What we're doing with this model is that we feed in the data, both their adjusted closing price and their corresponding sentimental scores of the first 4 days and heavily spit out the predicted adjusted closing prices of the last 3 days. Next, I will leave the stage for Wei to explain the details of Max model and the experimental result to you.
Okay, thank you, Jinlong. So in order to do comparison experiment with the aforementioned STM model, we also implemented a variation of typical ARIMA models, which we call Max models for short. As many of you may know, this is the mathematical expression for typical ARIMA models, the first row. And this is the model we used for our outlier detection. However, after the outliers and their associated rows were detected, we need to take into account the seasonality S and their exogenous variable X, which ended up with 5 more components added into the original formula, which you can see in the second formula. So we used a Python library called pyramid to select optimal parameters. And here is the detail in the screenshot. The reason we set maximum values for the parameters is to prevent overfitting, and the result itself showed that looking back at up to 3 lagged values is enough for the model to forecast accurately. And here is an example of how their AutoArima function found the optimal model for the airlines industry. Basically, it combined different values of PDQ, fitted the models into the training data, and returned the model with the minimum AIC. With the implementation details of the models in mind, let's move on to the experimental settings. This figure here is an example of the training and test datasets we feed into the LSTM and Max. Since our goal is to predict the adjusted closing prices of each stock, given that abnormal events already occurred, we only predicted the adjusted closing prices of the last 3 days. The accuracy is calculated by subtracting the mean absolute percentage errors from 1. Next, let's take Tesla as an instance. Here is the visualization of the result. The universal model denotes the model trained by the outliers of all stocks. The industry-wide model is the model trained by the outliers of the stocks in the same industry. As for the single stock model, it simply used a stock's own past outliers to train a model and then forecast its future values. Our interest here is not only to see whether training datasets would result in different predicted values for the same stock, but also to compare the performances of LSTM and Max models with their same training and test datasets. This is the reason why we had 6 figures over here, as you can see. Then here is the table comparing their accuracies and time cost by LSTM and Max. Technically, their number of epochs doesn't influence the accuracy of LSTM, but it does decide whether a model would converge or not. As shown in the table, the single stock model didn't converge when epoch is 10, but it took more time for the models to do forecasts when epoch equals to 1000, which we consider as unnecessary. Therefore, we think LSTM models with an epoch of 100 can best exemplify the performances of LSTM in this scenario. So we compare it to the Max model side by side in the second table. As you may already notice, the average accuracies of LSTM and Max are nearly identical, but LSTM is much more efficient than Max in terms of running time. Last but not least, here are our conclusions. Based on what has been presented so far, we think there are at least 3 conclusions we can infer from our results. First, from a perspective of accuracy and running time, LSTM outperforms Max when both models are trained with the same datasets. In addition, an average accuracy of over 98% also indicates that there is an underlying pattern of changes in stock prices under anomalous circumstances, and it is possible to capture the pattern by using one universal model. However, we will need to do further research in order to figure out what is inside the black box. Lastly, what are the possible applications of our model? Is it trivial? Well, to the best of our knowledge, although there are already some studies comparing the performances of LSTM and ARIMA models in time series analysis, none of them focus on predicting the adjusted closing prices of stock under anomalous circumstances by using sentimental analysis. Thus, we are confident to say that our study is non-trivial and believe that the results can be used to amend existing models. This is the end of our presentation, and the following are some references we used for this work. Thank you for listening.